Imagine yourself suspended in the middle of an invisible cosmic desert. Not the kind of desert you might know from Earth, but a bubble of emptiness so incomprehensibly vast that light itself, racing at 186,000 miles per second, requires 1 billion years to traverse its span. Every galaxy your telescopes can observe, every cluster of stars burning in the darkness, even the immense supercluster containing your home galaxy, all of it floats within this hollow. This is the KBC Void, the largest empty region ever discovered in the architecture of space itself. The numbers defy intuition. Recent measurements reveal something extraordinary. We are 100 million times more likely to be trapped inside this emptiness than living in what astronomers consider normal space. This void does not merely surround us. It fundamentally changes how the universe expands in our cosmic neighborhood. It bends the fabric of space-time. It alters the flow of time itself, making seconds tick differently here than in denser regions of the cosmos. For decades, astronomers avoided discussing what they were seeing in their data. They rechecked their measurements obsessively. They questioned whether their instruments had developed systematic errors. But the pattern refused to disappear. Something profound appeared to be wrong with our location in space, and confronting it meant challenging assumptions that had guided cosmology for nearly a century. In 2013, 3 researchers at the University of Hawaii, Ryan Keenan, Amy Barger, and Lennox Cowie, published findings that should have sent shockwaves through the scientific community. Their galaxy surveys revealed an undeniable truth. The Milky Way resides inside a region containing far fewer galaxies than theoretical models predict. This region measures roughly 1 billion light-years across, making it 7 times larger than typical cosmic voids. To put this in perspective, imagine the difference between a football stadium and an entire continent. That's the scale difference between ordinary voids and the one containing everything we can see without powerful telescopes. The void surrounds our galaxy completely. Everything visible in Earth's night sky exists within its boundaries. The Andromeda Galaxy, our nearest large galactic neighbor, located 2.5 million light-years away, floats in the same cosmic emptiness. The Virgo cluster, containing over 1,000 galaxies and representing one of the most substantial concentrations of matter in our region, occupies this same hollow. Even the Laniakea supercluster, a structure holding 100,000 galaxies, including our own, and spanning 520 million light-years, resides entirely within this cosmic desert. When astronomers measured the density of matter in our neighborhood and compared it to the rest of the observable universe, the results proved startling. Our cosmic backyard contains approximately 20% less matter than average space. This is not a minor variation or measurement error. It represents a dramatic deficit that persists across distances light takes hundreds of millions of years to cross. What makes this discovery particularly unsettling is the length of time it took to confirm. Astronomers harbored suspicions for years before the data became undeniable. Galaxy surveys showed peculiar gaps in distribution patterns. Distance measurements revealed unexpected structures. Yet accepting the truth meant acknowledging that our position in the universe violates a fundamental assumption underlying modern cosmology, the cosmological principle. This principle, refined over decades of observation and theory, states that on sufficiently large scales, the universe should appear essentially the same everywhere. No location should be special. No region should be dramatically emptier or denser than another when you average over large enough volumes. The universe should be homogeneous and isotropic, the same in all places and all directions. The KBC Void challenges this principle in ways that make cosmologists profoundly uncomfortable. Consider the scale. Average cosmic voids span roughly 140 million light-years. The void containing us measures approximately 1 billion light-years across 7 times larger than typical. Only one other void in the observable universe approaches this size, the Eridanus supervoid, which spans 1.8 billion light-years. Living inside such an enormous underdense region places humanity in a genuinely unusual situation. Most galaxies throughout the cosmos exist along dense filaments, or within massive clusters. They have countless neighbors. They inhabit matter-rich environments where gravity binds structures tightly together. We experience the opposite condition, profound isolation, surrounded by cosmic emptiness stretching almost incomprehensibly far in every direction. In 2017, another research team verified the original findings using completely independent methods. Benjamin Hogsett, then an undergraduate student working with Amy Barger, approached the problem from a different angle. Instead of counting galaxies directly, he examined the cosmic microwave background radiation, the ancient light released when the universe was only 380,000 years old. This radiation has been traveling through space for nearly 14 billion years, passing through every structure the universe has formed. As these photons traverse galaxy clusters, they experience subtle energy shifts called the kinematic effect. These shifts reveal how fast those clusters move through space. Hogsett's analysis was elegant. Galaxy clusters inside voids should move differently than clusters in normal density regions. They should be pulled outward by the stronger gravitational attraction of the denser matter surrounding the void, like marbles rolling toward the edge of a shallow bowl. When he measured these movements across our cosmic neighborhood, they matched void predictions with remarkable precision. The scientific community could no longer dismiss the findings as measurement artifacts or statistical flukes. Then came the most compelling evidence yet. In July 2025, researchers presented findings at the National Astronomy Meeting based on 2 decades of data studying baryon acoustic oscillations. These oscillations represent sound waves that rippled through the plasma-filled early universe before atoms formed. When atoms finally appeared and the plasma cleared, these waves froze into the distribution of matter like ripples fossilized in stone. Today, they act as cosmic rulers because their physical scale is precisely known from fundamental physics. The research team compared 2 scenarios. First, a universe where matter distributes uniformly and we occupy a typical, unremarkable location. Second, a universe where we inhabit a massive void that distorts local observations in specific, calculable ways. They asked, which scenario better matches 2 decades of observations? The statistical result was overwhelming. The void model proved 100 million times more likely than the uniform model to explain the data. In the language of statistics, this represents evidence so strong that maintaining skepticism becomes unreasonable. The universe appears to be screaming at us that we live inside something extraordinary, something that standard cosmology struggles to explain. To understand what cosmic voids truly are requires confronting a counterintuitive fact. Empty space is never truly empty. This confuses many people encountering the concept for the first time. These regions still contain galaxies, though far fewer than normal areas. They still contain dark matter, the invisible substance comprising most of the universe's mass. They still contain dark energy, the mysterious force driving cosmic expansion to accelerate. What makes them voids is relative absence, not absolute emptiness. Think of population density on Earth. Manhattan contains roughly 70,000 people per square mile, a concentration so dense that personal space becomes a luxury. Montana contains approximately 7 people per square mile, so sparse that neighbors might be separated by miles of open land. Montana is not empty of people, but compared to Manhattan, it qualifies as vast open space. Cosmic voids work on this principle at incomprehensible scales. Normal regions of the universe might contain 10 major galaxy clusters within a given billion light-year volume. A void might contain only 2 or 3 clusters in the same volume. The difference is dramatic without being total. Our void demonstrates this clearly. The Milky Way exists within it. So does Andromeda. The local group containing over 50 galaxies sits entirely within void boundaries. The Virgo cluster, one of the most substantial nearby galaxy collections, occupies void space. These structures prove the void is not completely empty. What makes it remarkable is the absence of the massive galaxy superclusters that dominate other cosmic regions. If you could see the universe from outside, normal regions would appear as brilliant, dense webs of light filaments and nodes where matter concentrates. Our void would appear as a darker bubble with scattered islands of illumination floating within. The density contrast measures precisely at 20% below average, a figure derived from careful surveys and painstaking calculations. Astronomers determine this by counting galaxies in expanding shells around our position. Close to us, within a few hundred million light-years, they consistently count fewer galaxies than cosmological models predict. Farther out, approaching 1 billion light-years, galaxy counts increase toward normal levels. Beyond that distance, the universe looks typical. The underdensity is localized to our region, not universal. But this underdensity has profound physical effects that ripple through everything we observe. Gravity depends on mass. Less mass means weaker gravitational attraction. In voids, the gravitational pull from the sparse interior matter is much weaker than the gravitational pull from the dense matter surrounding the void. Imagine a ball resting at the bottom of a shallow bowl. The bowl's walls pull the ball upward more strongly than the bowl's bottom pulls it downward. Galaxies and voids experience similar dynamics. They feel stronger attraction toward the void's edges than toward its center. This creates what astronomers call peculiar velocity fields motion that deviates from pure cosmic expansion. All galaxies have some peculiar velocity from local gravitational interactions with neighbors, but void galaxies have systematically outward peculiar velocities. They flee the emptiness, accelerating toward denser regions beyond void boundaries. Astronomers can measure these velocities by analyzing the light from galaxies, and the measurements confirm that galaxies in our region are indeed flowing outward, exactly as void dynamics predict. Understanding what the void truly means for cosmology requires accepting uncomfortable truths. Our location in the universe is unusual. The structures around us develop differently than structures elsewhere. The cosmic evolution we observe from our position may not represent typical cosmic evolution throughout the universe. We are measuring reality from an atypical vantage point, and that realization changes everything about how we interpret our data. When you zoom out far enough, the universe reveals its true architecture. What appears chaotic and random at small scales becomes organized and patterned at the largest scales. Galaxies cluster together into groups containing dozens of members. Groups combine into clusters containing thousands of galaxies. Clusters align along filaments, vast threads of matter stretching across hundreds of millions of light-years. Between these filaments, enormous empty regions dominate. Astronomers describe this pattern as resembling foam or the internal structure of a sponge, though the most popular comparison remains Swiss cheese. The cheese represents matter concentrated in filaments and nodes. The holes represent voids. This cosmic web grew through the relentless mathematics of gravitational attraction and depletion. Overdense regions attracted surrounding matter, growing denser. Underdense regions lost matter to nearby concentrations, growing emptier. The universe amplified its own tiny initial irregularities over billions of years. The structure emerged from microscopic variations in the very early universe. Right after the Big Bang, matter distributed almost perfectly uniformly but not perfectly. Random quantum fluctuations during the inflationary period created regions slightly denser than average and regions slightly less dense. These differences were minute, perhaps 1 part in 100,000. But gravity is an amplifier of inequality. Denser regions pulled in surrounding matter. As they gained mass, their gravitational pull intensified. They attracted even more matter in a self-reinforcing feedback loop. Meanwhile, the less dense regions lost their matter to nearby dense concentrations. As matter departed, these regions became progressively less able to hold on to what remained. They emptied systematically. After billions of years, the minuscule initial variations became the dramatic differences we observe today. Dense filaments now contain hundreds of times more matter than voids. The cosmic web represents gravity's masterpiece, sculpted over cosmic timescales. Scientists map this structure using galaxy surveys that observe millions of galaxies and measure their three-dimensional positions. From this data, researchers construct maps showing where galaxies cluster and where they are absent. The resulting images reveal the foam-like architecture clearly. Filaments appear as bright streaks connecting massive nodes. Voids appear as dark bubbles threaded through the structure. Our own position within a void becomes obvious in these maps, a dark region surrounded by brighter structures at its boundaries. The largest voids span over 1 billion light-years. The smallest voids, typically studied, measure around 100 million light-years. Most fall somewhere between averaging 200 to 500 million light-years across. These voids make up roughly 80% of the universe's total volume, yet they contain less than 10% of its matter. The universe is fundamentally an architecture of emptiness organized around thin threads of substance. The KBC Void ranks among the absolute largest voids ever detected. This matters because large structures are rare. The bigger the structure, the less likely it should be according to standard cosmological models. Finding ourselves inside one of the rarest structures in the observable universe raises profound questions about probability, observation, and our cosmic address. Living inside Laniakea illuminates our place in this grand architecture. Laniakea, meaning immeasurable heaven in Hawaiian, is the supercluster containing our galaxy. It spans 520 million light-years and contains the mass equivalent of roughly 100,000 Milky Way galaxies. For decades, astronomers believed the Virgo supercluster was our largest local structure. But in 2014, new mapping techniques revealed that Virgo is merely one component of the grander Laniakea supercluster. Crucially, Laniakea itself exists entirely within the KBC Void. This fact often gets overlooked, but proves essential to understanding our situation. The supercluster is not outside the void looking in. It represents one of the denser concentrations within the underdense region. Even Laniakea's relatively high density falls below the cosmic average when you account for the surrounding emptiness. The supercluster structure reveals void dynamics in action. Laniakea has a central gravitational focus called the Great Attractor, toward which nearby galaxies flow. But Laniakea as a whole moves toward an even larger structure beyond the void. The Shapley supercluster, one of the most massive concentrations of galaxies in the observable universe. The entire supercluster is being pulled outward, fleeing the void toward denser surroundings beyond its boundaries. We are passengers on a cosmic structure in motion, drifting through emptiness toward regions we cannot yet observe in detail. This motion has been measured. Our local group moves toward Shapley at approximately 600 kilometers per second, one of the largest peculiar velocities measured for any galaxy group. This extraordinary speed reflects the powerful gravitational pull of Shapley combined with the weak gravitational resistance from our underdense local environment. The void provides minimal anchor. Shapley pulls strongly from beyond the boundary. Our trajectory points directly outward from the void's interior toward its edge. In roughly 10 billion years, if these motions continue unaltered, the local group will exit the KBC Void entirely. We will enter the shell of dense matter surrounding the void, finding ourselves in a crowded supercluster region with countless neighbors instead of isolated emptiness. The contrast will be profound, transforming our cosmic environment completely. But 10 billion years represents an immense timescale. Stars will age and die, galaxies will evolve, and the Milky Way will collide and merge with Andromeda long before that distant future arrives. For now, we remain in our unusual position, living deep inside the largest void ever detected, not at its exact center, but close enough to experience its full effects. This positioning influences everything we measure about cosmic expansion, structure formation, and the universe's evolution. Whether that influence fully explains some of cosmology's deepest puzzles represents one of the most important questions facing astronomy today. The universe is expanding. Edwin Hubble discovered this revolutionary fact in 1929, transforming our understanding of cosmology forever. But knowing the universe expands is different from knowing how fast it expands. That expansion rate, called the Hubble constant, has become one of the most controversial numbers in all of physics. Scientists measure it using two different methods, both rigorous and extensively tested. The problem? They give different answers. The disagreement has grown so severe that physicists call it the Hubble tension, and it threatens to shatter our understanding of cosmic evolution. The first method examines the early universe through the cosmic microwave background ancient light released when the cosmos was only 380,000 years old. This radiation carries detailed information about the early universe encoded in tiny temperature variations. By analyzing these patterns using standard cosmological models, scientists calculate how the universe expanded from that ancient time until now. This method predicts the current expansion rate should be approximately 67 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, space expands fast enough to carry galaxies 67 kilometers per second farther apart. The second method examines the local universe directly using Type Ia supernovae exploding stars that shine with predictable brightness. By comparing how bright these explosions appear versus how bright they should be intrinsically, astronomers calculate their distance with remarkable precision. They also measure how fast these distant galaxies move away by analyzing the redshift in their light spectra. Combining distance and velocity yields the expansion rate. This method consistently produces values around 73 kilometers per second per megaparsec. 6 units of disagreement might seem minor, but it represents approximately a 9% difference. In physics, when two independent, well-tested measurement methods disagree by 9%, something is seriously wrong. Either the measurements contain unknown systematic errors, or our theoretical understanding is fundamentally flawed. Physicists have scrutinized both methods exhaustively. The measurements appear robust. The theory must be incomplete or wrong. This tension has persisted for years and grows stronger as measurements improve. More data makes the disagreement more statistically certain, not less. Scientists have proposed numerous explanations. Perhaps dark energy behaves differently than current models assume. Perhaps neutrinos have unexpected properties. Perhaps gravity operates differently at cosmic scales than Einstein's general relativity predicts. None of these ideas fully resolve the tension without creating new problems elsewhere. But there exists another possibility, one that has gained serious attention as void evidence accumulates. What if the difference arises not from our theories or measurement techniques, but from where we are making the measurements? What if our location inside a massive cosmic void distorts what we observe? Local measurements would reflect void dynamics, the unusual expansion behavior of underdense regions. Early universe measurements would reflect average cosmic conditions. The two would naturally disagree, and the disagreement magnitude would depend on the void's size and depth. This explanation has gained traction because the void we inhabit proves large enough and deep enough to create exactly the observed discrepancy. The void might be hiding in plain sight, masquerading as a crisis in fundamental physics when it actually represents a crisis of location. Gravity pulls matter together. This simple principle dominates cosmic evolution, but inside voids, gravity creates a paradox. With sparse matter present, gravitational attraction from the interior weakens dramatically. The void's surroundings, dense with matter, pull much more strongly. For galaxies trapped inside, the outward pull wins. They accelerate away from the void's center, toward its denser edges. This movement creates an observational illusion that confounds measurements of cosmic expansion. Picture a galaxy sitting in our void. The sparse matter inside pulls on it weakly. The massive shell of galaxy clusters surrounding the void pulls on it powerfully. The galaxy moves toward that shell, fleeing the emptiness. From our perspective, watching from inside the same void, this galaxy appears to recede faster than cosmic expansion alone would drive it. We interpret this excess velocity as faster expansion. We calculate a higher Hubble constant. Our local measurements become systematically biased. The effect compounds with distance. Galaxies farther from us experience stronger acceleration as they approach the void's edge, where density gradients steepen most dramatically. Very distant galaxies beyond void boundaries experience normal cosmic expansion without the void's distorting influence. Our local universe appears to expand faster than the distant universe, exactly what astronomers observe when comparing local and early universe measurements. Indranil Banik, a cosmologist at the University of St. Andrews, led recent research quantifying this effect precisely. His team calculated how matter flows in and around large voids using sophisticated models. They determined how these flows alter astronomical observations. For a void approximately 20% less dense than average and roughly 1 billion light-years across, the observational distortion reaches precisely the magnitude needed to explain the Hubble tension. If we sit near the center of such a void, our measurements would systematically overestimate the true cosmic expansion rate by about 9%. The agreement with observations is remarkable and difficult to dismiss as coincidence. But the void creates other observable effects beyond velocity measurements. Light traveling through voids experiences gravitational redshift differently than light traversing normal regions. Photons lose energy climbing out of gravitational wells. The deeper the well, the more energy lost. In voids, the gravitational wells are shallow. Less energy loss occurs. This subtle effect alters how we calculate distances from brightness measurements, creating another source of systematic bias. Time itself behaves strangely in voids. General relativity demonstrates that gravity affects how fast time passes. Stronger gravity means slower time. In dense regions filled with matter and deep gravitational wells, clocks tick more slowly than in empty regions with shallow wells. Over billions of years, this difference accumulates significantly. Regions in voids may have experienced more elapsed time than regions in dense areas, even though both started simultaneously at the Big Bang. This concept challenges the comfortable assumption that the universe has a single, universal age everywhere. Different regions may have different effective ages depending on their matter density history. These time differences affect how we interpret cosmic evolution. When we observe distant galaxies, we see them as they appeared billions of years ago, but exactly how many billions depends on assumptions about how uniformly time has flowed. If voids experience accelerated aging compared to dense regions, our cosmic timelines need recalibration. The universe might be older in some places and younger in others, creating a patchwork of temporal variation across the cosmos. The implications grow more disorienting the deeper you examine them. Everything cosmology assumes about measuring distances, ages, and expansion rates may require fundamental recalibration if we truly inhabit a supervoid that distorts observations in multiple, compounding ways. Sound waves froze into the fabric of space. This statement sounds like science fiction, but describes real physics with profound implications. In the universe's first few 100,000 years, matter existed as hot, dense plasma. Pressure waves rippled through this plasma at roughly half the speed of light. These waves were genuine sound, traveling through a medium that filled all of existence. Then, the universe cooled. Atoms formed. The plasma vanished, becoming transparent. The sound waves stopped propagating and became permanent features frozen into how matter distributed across space. Today, we observe these frozen sound waves as statistical patterns in galaxy arrangements. Galaxies are slightly more likely to be separated by specific distances corresponding to how far the original sound waves traveled before the plasma cleared. These patterns are called baryon acoustic oscillations, baryons being the protons and neutrons comprising normal matter, acoustic referring to sound, and oscillations meaning waves. Together, the term describes sound waves in normal matter from the early universe, now fossilized in the cosmic structure. These oscillations provide a cosmic ruler of known size because fundamental physics tells us precisely how far the waves traveled. By measuring how large this characteristic scale appears at different distances and cosmic epochs, astronomers can determine how the universe has expanded over time. It works like recognizing a meter stick and using it to judge distances and sizes of other objects. The oscillations act as standard rulers scattered throughout cosmic history and space. Indranil Banik and his collaborators analyzed 2 decades of baryon acoustic oscillation data, comparing 2 competing scenarios. First, a universe where matter distributes uniformly, and we occupy a typical, unremarkable location. Second, a universe where we inhabit a large void that systematically distorts local observations in specific, calculable ways. They calculated which scenario better matches the observed patterns in galaxy clustering across vast cosmic distances. The statistical result proved stunning. The void model proved 100 million times more likely than the uniform model to explain the data. 100 million is not a minor statistical preference. It represents evidence so overwhelming that maintaining doubt becomes scientifically untenable. In statistics, even a factor of 100 makes a conclusion essentially certain. A factor of 1 million would be categorically decisive. 100 million represents evidence so powerful that the data appears to be screaming the truth at us. We live in a void, and that void profoundly affects everything we observe. The baryon acoustic oscillations reveal subtle distortions in galaxy clustering that only a void geometry can explain. In a uniform universe, the oscillation patterns should appear identical in all directions and at all distances. Instead, the patterns show systematic variations matching predictions for an underdense region. Galaxies in certain directions cluster slightly differently than galaxies in other directions. The differences align precisely with void geometry expectations. The data contains a signature that cannot be explained by random chance, measurement error, or alternative theoretical models that assume uniformity. Additional confirmation emerges from comparing observations at different redshifts, which correspond to different distances and look-back times. Nearby observations should show stronger void effects than distant observations, because distant observations see beyond the void's boundaries into normal density regions. The data exhibits exactly this pattern. Local structure appears more irregular and sparse. Distant structure appears more uniform and typical. The transition occurs at roughly the distance where the void's edge should lie, based on other measurements. Another remarkable agreement that strengthens the case. Multiple independent research groups using different analysis methods reach similar conclusions. The evidence continues accumulating from every direction astronomers look. Yet accepting the void means accepting that the cosmological principle which states that no location in the universe should be observationally special does not hold at the largest scales accessible to current observations. That principle has guided cosmological thinking for nearly a century. Abandoning it requires extraordinary evidence. The evidence now qualifies as extraordinary by any reasonable scientific standard. The void is real. We live inside it. And it matters profoundly for understanding what our observations truly tell us about the universe of weakening. All evidence suggests it remains constant or possibly strengthens. If it strengthens, the consequences become catastrophic. In scenarios called phantom energy, or big rip models, dark energy intensifies until it tears apart all bound structures. First, galaxy clusters unbind as space between member galaxies expands too rapidly for gravity to hold them. Then galaxies themselves dissolve as stars are ripped away. Solar systems disintegrate as planets escape their orbits. Eventually, even atoms are torn apart as space between subatomic particles expands faster than forces can bind them. The universe ends not in cold emptiness, but in violent disintegration. Current measurements do not support this extreme outcome, but they cannot rule it out completely. The uncertainty in dark energy's equation of state leaves room for disturbing possibilities. Voids would accelerate this process if it occurs. They already expand rapidly. If dark energy strengthens, void expansion accelerates further. Void boundaries dissolve faster. The merger of neighboring voids happens sooner. The universe transitions more quickly into void-dominated geometry. Our position inside the KBC Void means we would witness these changes earlier and more dramatically than observers in dense regions. We are at the frontier of cosmic emptying. What happens here previews what will eventually happen everywhere. In this sense, studying our void is studying the universe's future. The dynamics we measure today foreshadow the dynamics that will govern all of space billions of years from now. But billions of years provide little comfort when confronting existential questions about cosmic fate. The void reminds us that structure is temporary. Organization emerges from gravitational collapse over billions of years, but expansion tears it apart over longer timescales. Entropy increases, isolation grows. The arrow of time points toward emptiness. Voids are not aberrations, they are the destiny of space itself. Yet within this bleak trajectory, islands of complexity persist for immense durations. Stars will continue forming for trillions of years. Galaxies will host stellar populations and planetary systems. Life, where it emerges, can flourish for timescales that dwarf the current age of the universe. The heat death lies so far in the future that it bears no relevance to anything happening now or in the foreseeable future. The void expands, but life adapts. Consciousness observes. Understanding accumulates. The question that haunts cosmologists is whether our understanding is fundamentally limited by where and when we exist. If we live in an unusual location at an unusual time, can we ever discern universal truths? Or are we condemned to constructing theories that work locally but fail cosmically? Observational astronomy reveals only what light allows us to see. Light has a finite speed. It travels through an expanding universe. The combination means we cannot see beyond a certain horizon, the cosmic event horizon defined by where space expands faster than light approaches. This horizon shifts with time. It encompassed more space in the past when expansion was slower. It encompasses less space now as acceleration intensifies. In the distant future, it will encompass only nearby structures. Everything beyond this horizon is inaccessible. We cannot observe it. We cannot detect signals from it. It might as well not exist as far as empirical science is concerned. Yet it presumably does exist, following the same physical laws, evolving according to the same dynamics. We are simply cut off from it by the limitations of light speed and cosmic expansion. The void complicates this picture further. If we inhabit an unusual region, our observations may not represent conditions beyond our horizon. The universe outside the void might be denser, more structured, evolving differently. We cannot know because we cannot see it. Our cosmological models are built on the assumption of uniformity. What we see here reflects what exists everywhere. If this assumption fails, our models fail. This limitation is not unique to cosmology. All science operates under constraints. Biologists study life on Earth and extrapolate principles they hope are universal. Physicists study matter and energy accessible in laboratories and assume fundamental laws do not change elsewhere. The assumption of universality underpins the scientific method. Without it, knowledge becomes impossible because every situation would require its own unique explanation. But the assumption remains an assumption, not a proven fact. Testing it requires comparing observations from different locations and times. In cosmology, we have only one location Earth, inside the Milky Way, inside the local group, inside Laniakea, inside the KBC Void. We have multiple times because we see the universe at different epochs when observing different distances. But location variation is impossible. We are stuck here. We must infer what exists elsewhere from limited vantage points. The void hypothesis forces confronting this limitation directly. If our location biases observations significantly, cosmology requires recalibration. We must disentangle genuine cosmic properties from location-specific artifacts. This is difficult, but not impossible. The key lies in comparing local and distant measurements and understanding how they should differ if location matters. The Hubble tension is precisely this kind of comparison. Local expansion rates differ from early universe expansion rates. The difference could be location effects, Sophisticated statistical methods can test whether observations are consistent with uniform cosmology or require accounting for voids. Bayesian analysis, which compares how likely different models are given the data, has become standard practice. The 100 million to 1 odds favoring the void model in recent baryon acoustic oscillation analyses represent exactly this kind of test. The data are far more likely if we live in a void than if we do not. As measurements improve, confidence grows. If multiple independent tests all reach the same conclusion, location effects become established facts rather than speculative hypotheses. Science is never completely certain, but it can achieve high confidence when evidence accumulates from many directions. The void is approaching that threshold. A few more years of data may settle the question definitively. Yet, even if the void is confirmed, mysteries remain. Why is it so large? How did it form? Why are we inside it? These questions may have answers rooted in statistics and cosmic evolution, but they touch on deep issues about probability, observation, and existence. The universe is full of rare structures, and observers must exist somewhere. Perhaps observers preferentially exist in unusual locations for reasons we do not yet understand. Perhaps life requires certain environmental conditions that correlate with void properties. These are speculative ideas, but they illustrate how discovering we live in a void opens philosophical questions alongside scientific ones. The void also highlights the difference between what exists and what we observe. The universe presumably has an objective structure, a true arrangement of matter and energy independent of observers. But what we observe is always mediated by light, instruments, and analysis. Observations are not direct access to reality. They are data filtered through multiple layers of physics and interpretation. Understanding these filters is essential for inferring reality from observations. Voids affect observations in multiple ways. They alter peculiar velocities, creating systematic patterns in galaxy motions. They change gravitational potentials, affecting time dilation and photon energies. They modify expansion rates locally compared to globally. They create selection effects in what we detect and how we interpret it. Disentangling all these effects requires careful modeling and analysis. But it is possible. The physics is understood even if the calculations are complex. This understanding provides hope that cosmology can overcome the void challenge. If we can measure the void's properties precisely, we can correct for its effects in our observations. Corrected observations would then reveal the true underlying cosmic properties. We would know both our local environment and the universe's global structure. The void becomes an interesting feature to study, rather than a confounding factor to worry about. Some scientists even suggest the void could be advantageous for certain observations. Its low density reduces foreground contamination when observing distant objects. Its key gravitational environment simplify interpreting large-scale dynamics. Its well-defined geometry provides a laboratory for testing cosmological models. Once understood, voids become tools rather than obstacles. The ultimate goal of cosmology is understanding the universe's origin, evolution, and fate. Living in a void does not prevent achieving this goal. It merely requires recognizing where we are and accounting for it appropriately. The Copernican principle that we do not occupy a special location must be refined. We do not occupy a privileged location in the sense of being the center or having unique significance. But we may occupy an unusual location in the sense of being statistically rare. Unusual is not the same as privileged. It just means we must think carefully about what our observations tell us. This distinction matters philosophically and scientifically. For centuries, humanity has progressed by realizing we are not special. Earth is not the center of the solar system. The sun is not the center of the galaxy. The Milky Way is not the center of the universe. Each realization has been humbling, reminding us that we are small parts of something vastly larger. The void continues this tradition. We are not privileged observers. We are ordinary observers, in an unusual location. The universe does not care about us or our convenience. We must adapt our understanding to match reality rather than expecting reality to match our assumptions. Yet this humility empowers rather than diminishes. By recognizing limitations and biases, we can compensate for them. By understanding our environment, we can see past it to the larger cosmos. Knowledge grows through correcting errors and refining models. The void is an error to correct and a model to refine. It is not a barrier to understanding, but a step toward it. Future historians of science may look back on the early 21st century as the era when cosmology matured by confronting the void. Earlier cosmology assumed simplicity, uniform expansion, homogeneous matter distribution, typical observing conditions. Modern cosmology embraces complexity, lumpy structure, varied environments, location-dependent observations. This transition is healthy. It represents science engaging with reality in its full complexity rather than oversimplified models. The void teaches that the universe is more intricate than our theories assume. This lesson has been learned repeatedly throughout scientific history. Newton's laws worked beautifully until they did not fast velocities, and strong gravity required Einstein's corrections. Einstein's general relativity works beautifully except at quantum scales where it breaks down. Every successful theory has limitations and eventual replacements. The current cosmological model will be no exception. Perhaps dark energy will be explained as a void effect, eliminating the need for mysterious new physics. Perhaps modified gravity will replace general relativity at cosmic scales, resolving multiple tensions simultaneously. Perhaps neither, and the solution will be something completely unexpected. The void is a clue, but the full picture remains obscured. More data, more analysis, and probably more surprises await. What is certain is that the question will be answered. Science does not remain uncertain forever about answerable questions. Measurements will decide. The void either exists as a significant structure affecting cosmological observations, or it does not. Either it explains the Hubble tension, or it does not. Either we live in an unusual location requiring special consideration, or we do not. These are empirical questions with empirical answers. The answers will arrive within the next decade or two as observations accumulate and improve. When the answers arrive, cosmology will change. If the void is confirmed and explains major anomalies, textbooks will be rewritten. Cosmological calculations will include void corrections. The cosmological principle will be refined to allow for large-scale fluctuations while maintaining statistical homogeneity over even larger scales. Dark energy might be reinterpreted or eliminated. Our cosmic address will become part of every cosmological discussion. If the void is refuted or proves less significant than current evidence suggests, the search continues for alternative explanations. The Hubble tension remains. The baryon acoustic oscillations still show puzzling patterns. Something is wrong with our understanding, and if not the void, then what? New physics will be needed. New theories will be developed and tested. Science will progress through this process as it always has. Either way, the void has served a crucial function. It has forced cosmologists to question assumptions and consider seriously that observations might be location-dependent. This questioning is healthy. It strengthens science by making it more critical and rigorous. Assumptions should always be questioned. Models should always be tested. Data should always trump theory. The void controversy exemplifies these principles in action. You are standing in the middle of an invisible cosmic desert, a bubble of emptiness so vast that light requires 1 billion years to traverse it. This void shapes everything you observe about the universe: how fast it expands, how structures formed, how time flows, and perhaps even whether life could emerge and thrive. Scientists have measured its properties with increasing precision. They have calculated its effects with increasing sophistication. The evidence mounts that this void is real and significant. Yet profound questions remain. Why is it so large? How common are such voids throughout the cosmos? What does living inside one teach us about the universe's fundamental properties? Do voids like ours affect observations in ways that mimic dark energy or modified gravity? Can we ever disentangle what is universal from what is local when we have only one observing position? These questions define the frontier of modern cosmology. They require new observations, better simulations, deeper theoretical understanding. They demand humility about what we know and honesty about what remains uncertain. The void is not merely an astronomical curiosity or a technical correction to cosmological calculations. It is a window into understanding how complex and surprising the universe truly is. For now, the void remains partially mysterious, its full implications still being calculated and debated. But the mystery is being solved through the patient accumulation of evidence and the rigorous application of scientific method. Nature holds the answers. Humanity has the tools to find them. The question is not whether we will understand the void, but when and what that understanding will reveal about the cosmos and our place within it. The journey through this cosmic desert has only begun. Each new measurement brings us closer to truth. Each refined analysis clarifies the picture. The void that once seemed like an embarrassing anomaly now appears to be a crucial clue about cosmic structure and evolution. What we learn from studying this emptiness may ultimately teach us more about the universe than studying the densest, most spectacular structures could ever reveal. Voids are where the universe shows its simplest face, where matter has fled, where gravity weakens, where expansion dominates. In this simplicity, fundamental processes become visible without the complicating factors that obscure them in dense regions. The void is a laboratory for cosmology, and we are fortunate to reside within it. Our unusual address provides an unusual perspective, and unusual perspectives often lead to the deepest insights. So here we are, inhabitants of a galaxy floating through one of the largest cosmic deserts ever discovered, measuring the universe from a location that biases almost everything we see. It is a strange and humbling realization, but it is also an opportunity, a chance to understand not just the universe in general, but our specific relationship to it. By accounting for where we are, we can finally see past our location to the larger reality beyond. The void is not an obstacle to knowledge. It is a challenge that, once met, will deepen our understanding immeasurably. The cosmic desert stretches around us in all directions, vast and empty, slowly expanding as dark energy drives space itself apart. Galaxies flee its interior, structures thin and disperse. Time flows faster here than in denser regions. And from within this emptiness, conscious beings look outward, asking questions, gathering data, building theories, and slowly, methodically, figuring out where they are and what it means. That is the story of the void, and it is our story, written in the architecture of space itself.